Okay, so good evening, everybody, and welcome to our class. We have for today, the topics we want to cover are the following. Essentially, in our last class, we didn't quite get to the normal distribution, and it was a bit much to try to cover at that last moment. I'm hoping you had a chance to watch the video lecture on it. And then I will introduce you to the topic in chapter 7, which has to do with what we call sampling distributions, okay? So tonight we will try to cover 6.2, 7.3 to 7.5, and 7.6. It is a bit much to try to cover in one night, but we'll try to see how far we get. And if it means that we have to supplement what we do tonight with some video material, then we'll try to do that for you. All right. Before I go any further, the first assignment was done. The average on that first assignment was, I believe, 84%, which was good. Not sure if anybody have any questions or concern at this point. So.
I have a question about the assignment.
Yes.
So typically, like I know this is an online course, it's not your typical like go to class, come home kind of thing.
Yes.
But I'm wondering if it's up for consideration. Like I felt the assignment was extremely long and it's definitely doable, but I mean, it's kind of unrealistic in the way that usually if you were assigned something, you would have the week to kind of chip away at it, work at it, where this one, once you begin, you have to do it in that exact time and you can't come back.
Oh, no, I believe you are able to save and then continue. Come back to the assignment, as far as I know.
From the instructions on it, it doesn't look like you can do that. It says if you are timed out, it will save it for a minute, but if not, like that's your first attempt.
Okay, I'll double check that because for a test, when the test is timed, then basically the clock is running. But with an assignment, you should be able to save your answers and go back and, so in other words, do it over a period of time because there's really no time limit on completing that assignment.
Yeah,
except for a due date. Yeah.
Okay, I don't know if anybody else had that impression too, but when I looked on the instructions, it basically said if it timed out that you could go back to it. If not.
Yeah, actually, there's no timeline. I do that for 2 days. It's fine.
Oh, really? Okay.
Yeah.
Yeah, basically you can start the assignment now with question number 1. Save your answer. Don't submit yet. I don't think you shouldn't submit it.
Yeah, just push the save. That's all.
Okay, great.
Button. And then go back. When you go back, then it has your save answers, and then you continue. It is when you really have the timed assignments like the tests and so on.
Exactly.
Then that's it. Pretty much your clock runs, right?
Okay, great. That's
okay. No problem. Thanks for bringing that up. Anybody else? Any other questions?
I had a question about reading the graph.
Sure, go ahead, please. I can't hear you very well.
When you go into the graphs,
yes.
So you just take you just round it off, or you do interpolate it. The way the results came back on when I did the first set of assignments, they rounded down when they went into the graph. They didn't extrapolate in between the two numbers.
Okay, so you're talking about the assignment, or you're talking about the normal distribution that we're about to talk about?
The assignment.
Okay, so maybe what you can do, if you could tell me, because there are different types of graphs, right? If you're talking about bar charts, histograms, cumulative distributions, and so on.
I'm talking about the tie chart, I believe it's called.
Sorry?
I'm a little messed up on the terminology. But, if you're doing the assignment, you can open up the table.
Uh-huh.
When you go into that table,
yes,
the number you calculated, use that number to extrapolate your data.
Yes.
They were rounding, the number that you're using to win, they were rounding that number. I thought you had to extrapolate.
Oh, okay. So what if you want to look at that, do you remember like what one question that I'm trying to, so I could actually look at that specific issue?
No, so for example, if you were in there and you're reading 1.2 1.28.
Yes.
If you had one in your calculation, you had 1.24.
Yes.
They just used 1.28 instead of doing 1.28 or 1.29.
Okay.
Just want to make sure that was okay for the final.
Well, one of the things that I can do, if there is now with the assignments, I put in a tolerance on the answer. So say, for example, your answer should be 1.25. I usually put in like about a 5 to 10, I think it's maybe 5% tolerance on the answer, so that if you're off by a few decimal points, it should not grade you incorrectly. I'm not sure if that's what you're referring to.
I can send you an email and probably better
Yes, please.
explain.
Yeah, let's do that, and then I could take a look at it. Okay. And if you could point to which question on your assignment that refers to, then I could certainly take a look at that.
Okay.
All right, no problem. Anybody else? Any other questions? Okay, so let's get started with today. So I'm continuing from actually our last class, because like I said, we had quite a bit of material, and I want to introduce you to the normal distribution, and then we're going to talk about sampling distributions. So I'm going to I know that you are supposed to watch the video ahead of time just to kind of give you some basic familiarity, but I'm going to sort of do a quick review of that and then work a problem or two, okay? So let us take a look at the chapter on the section, on normal distributions. So what is a normal distribution? And many of you have heard of, I'm sure, the term bell curve, the bell curve. That curve that is very symmetrical. And that bell curve has an official name, which is called the normal distribution. It's a very popular distribution in statistics because there are so many different random variables that can be modeled using the bell-shaped curve. So for example, if we take heights of people, right? This bell-shaped curve, the way in which it's shaped, essentially you have, for example, a small set of values or low frequencies down in the tails, but then you have a huge frequency in the middle, all right? So that means that's where most of your values are, but in the upper tail and the tail below, you have fewer and fewer values. So let's just see how that applies in some real situations, right? So if you think of heights of people, and you had a random sample of people of all ages, if you actually check their heights, you may find there's a small frequency of very short people, a small frequency of very tall people, and most of us are somewhere in the middle, maybe between 4 feet, 4 feet 6 inches to 5 feet 6 inches, somewhere in that middle range. But you'll get a small portion of people that are very short and a small portion of people very tall, and most of us are in the middle. Think of test scores. So test scores is not uncommon to find a small percentage of the folks who did the test who have very high marks, a small percentage of them who have very low marks or may have failed, and then most of us are somewhere in the middle. On a test, maybe we got between 60 and 80, you know? And very few students got like 90 and above, very few students got 30 and below, or 20 or 40 and below, and so forth. So that kind of conforms to the shape that we call the normal distribution. Amounts of rainfall or snowfall, for example, we may have, if we look at annual rainfall, and we look at it maybe on a daily basis, or a weekly basis or something like that, you may very well find that you have a few periods where you had very high amounts of rain, a few periods where you had no rain at all, and perhaps in the middle is where you have, the average amount of rainfall. Either if you look at it as monthly rainfall or weekly rainfall and so on, we'll find a number of values in the middle. So as a result of that, this distribution, like I said, is very, very popular. And one last one would be like salaries, right? So if you look at maybe an industry, you may very well find, or let's say computer science or engineering or law, whatever, business. You may find, if you want to kind of narrow things down to a particular industry and so on, you may find, if you're looking at salaries, that there are few people who make very, very high salaries, you know, six-figure salaries and so on, over $200,000 a year. And then you may find that there's a very low number of people who make very small salaries. I don't know, perhaps like, you know, $15,000 a year or less or whatever. And then most of the values, in terms of most of the salaries, are somewhere bulged in the middle. So that's another example in terms of salaries that we could find, right? So given that, we want to kind of learn how to use the normal distribution. Now, the normal distribution is a continuous distribution. By continuous, what we mean is that it can take on an infinite number of possible values. An infinite number of possible values. So often when we are interested in finding probabilities with the normal distribution, we are really interested in a region under that curve. So if, for example, the average grade in a final exam in statistics is 65, I could say to you, what is the probability that a student gets above 75? So that would mean 75 or more. That's a range of values. What's the probability that a student gets below 60? That's a range of values. Or what's the probability that a student can get between 55 and 85? That's a range of values as well. So as a continuous distribution, we're never interested in the probability of a single value. We're interested in the probability of a range of values. I'm just going to share my my iPad with you here for a second. So if we look at this, so if we have a normal distribution, a shape like that, oh, not very cool. It's better. So it has a mean, which we denote by mu, and a standard deviation, sigma. We are interested in a range of values. So the random variable will be x. That's the random variable. And we could say, what's the probability that we have an observation that is greater than x is 0? So we'll say the probability of x greater than or equal to x0. So the random variable is x, and the value of that variable is x0, whatever that is. So for example, if we say that 65 is the average mark of a student, the standard deviation is 15, I could be asking you, what's the probability that a student will get a mark greater than or equal to 80? So probability of x greater than or equal to 80, all right? So that's that region right here. If I say probability of a student getting less than or equal to 50, so that is 50 is below the 65, so it should be on the left-hand side, and that will be that area right here. And then if I'm interested in the probability of, say, a randomly chosen student getting between 50 and 80 for this distribution, then I'm talking about this region right here, right? So we are interested in ranges. Question is, how can we find these probabilities? Now, because this is a continuous distribution, meaning that it can take on, the x variable can take on an infinite set of values. That means x can be between negative infinity and positive infinity. So that's a continuous distribution. To get areas under the curve, we'll have to do some calculus, integration. But we've not done integral calculus at all. We've done differential calculus in 1206. but we would have to actually do integral calculus. Integral calculus is actually the reversal of differential calculus. But that's a little difficult. We don't really want to have to do that. So what's an approach to handling that situation? How do we do it? Well, the way in which we do it is that we try to find a distribution that's equivalent to this one, but that gives us the area under the curve that corresponds to what we are looking for. And that particular distribution is called a standard normal. So if this is the normal distribution, there is a distribution called the standard normal distribution. That standard normal distribution is such that the area under the curve will be equal to 1. The total area under the curve is equal to 1. So if the total area under the curve is equal to 1, then any of these colored portions that you see in my diagram, this portion right here, or this portion, they would all be less than 1. So let's just say, for instance, that this area here is 25%, 0.25. So it's less than 1, so 0.25. So that means 25% of all of the values are in the range greater than or equal to 80. So if I wanted to ask you what's the probability of x being greater than or equal to 80, that would be 0.25. That's because 25% of all of the values are in that range. Right? If in between 50 and the 80, that was, say, for example, 55% of the value, let's say that was 0.55 or 55%, then the probability of being between, 50 and 80 would be 0.55. Right? That means 55% chance of being in that range. If I was interested in the red region, what if that were 25 and 55 is 80? So that's 20%. So what if I was interested in less than 50? Then in that case, the probability of x less than or equal to 50, if that area corresponds to 0.20, then that probability would be, 20%. So there's a 20% chance that there's a 20% chance that you can get a value with 50 or less. All right. Now, with a continuous distribution, we are never interested in the probability of an exact value. So, for example, if you say, what's the probability of x being equal to 80? What's the probability of x equal to 80? So, technically speaking, we could say the definition of a probability is the number of favorable situations divided by the total number of possibilities. Well, x equal to 80 just have one favorable situation. But because we say it's a continuous distribution, there's an infinite number of possible values. So 1 over infinity would be equal to 0. So as a result, we're never really interested in the probability of an exact value. We are always interested in the probability of a range of values, like x less than or equal to 50, or x between 50 and 80, x between greater than or equal to 80, and so on. All right? So, and how do we get that area under the curve without doing all that fancy calculus? Well, here's how we do it. So, as I mentioned to you, for every normal distribution, there is an equivalent standard normal. So the normal distribution will have the parameters mu and sigma, which basically means that's the mean of the distribution and the standard deviation of the distribution. And to get the standard normal, it's like a scaled version of that very same normal distribution. So our random variable here is x, and here, that mu turns out to be 0, the standard deviation turns out to be 1. The random variable for this distribution, which is the standard normal, and this is the normal, we use z as the random variable, and here we use x. So it turns out that the area under the standard normal is equal to 1. That's the characteristic of the standard normal. But how do we go from the normal distribution to the standard normal? Because what happens is that if we know how to go from one to the next, it's like converting feet to inches. We multiply feet by 12. Converting meters to centimeters, we multiply by 10, and so on. So it's like there's a conversion from a normal to a standard normal. And what is that conversion process? So, and because if we can do the conversion, anytime we have a value here, which is an x value, let's call it x0, it has a corresponding z value, z0. So there's a corresponding z value, which means that what this area here represents in terms of the normal distribution is the same proportion that it represents under the standard normal. But because the standard normal has an area of 1, any area under the standard normal, any part of that will be less than 1. So if that were 0.3, then it means that this area in red is 30% of the original distribution, all right? So how do we go from one to the next? This is how we do it. For every x value, there's a corresponding z that can be calculated using this formula, x minus the mean over the standard deviation. And folks, what I should remind you of is what we did in chapter 3, which is called a z-score. What was a z-score? A z-score was the difference between the x value and the mean of the distribution expressed in standard deviations. So that is the z-score right here. And so if we know the z-score, then what's the value of that to us? Well, the value of that to us is that we have a table. We have a table that will actually allow us, if we know the z value, it will allow us to find areas under the curve, all right? And that's where the beauty of the standard normal comes in, is that we have a table that gives us, if we give it the z value here below the midpoint, if we give it that z value, we'll get that area. Now, because the standard normal, the mean of it is 0, any value below that 0 will be negative. So those values will be like negative z values, all right? So we may have 0, 0.1, 0.2, 0.3, etc., but it would be negative 0, negative 0.1, right? Because those values of z are below the 0 point. And we'll get the area under the curve. So in here, we will get areas. I'm going to show you that diagram just now, right? But the book also gives us the positive case, which is here. It will tell you if you have a z value above that 0 point, the table will give you this area right here, the cumulative area, right? So those values of z above the 0 mark will be positive. And so we'll have 0, 0.1, 0.2, 0.3, and so on, and we will have an area here. That area will represent the shaded region. The areas here would represent that shaded region, right? So we're going to have to learn how to use the table. So essentially, anytime we have a problem where a z value is involved, we could go to the standard normal table and calculate the area associated with it. So let's see if we can take a look at what that table looks like, right? I'm going to try to bring that up from my desktop, so bear with me a second. And we want some tables. Where is it? It's disappeared on me. Give me 1 second, I'll find it. Where are my tables? Okay. Tables, there we go. All right. So, and then I'm going to stop this share. I got to keep switching back and forth between different things on my desktop to share with you. So you'll see that happen from time to time. Okay. So here we go. We have our Z table. And if you have your book with you or your ebook in MindTap, you could certainly get to the Z table. So here's the case where this is the standard normal. You see here standard normal distribution. The mean of the standard normal is 0. Its standard deviation is 1. And it's a bell-shaped curve, just like a normal distribution. So whenever we get a Z value, so in this case, those Z values are negative. So you see here, if it turns out that, say, for example, the Z value is negative 2.92, so somewhere down here, then if we look up negative 2.9, the second decimal place is on the top. So that means that the area, which would be that shaded region right here, is 0.0018. If we express that as a percentage, it would be 0.18%, a very small area. Let's just see if we were to take, for example, 0.15, negative 0.15. So negative 1.15, just a random value. So again, because the negative value is below the 0 mark, we'll get the shaded region right here. Negative 1.1, and if we go to 5, 5 is over here. The second decimal place, we come down. Negative 1.15 is this value right here, corresponds to this area, which means that if your Z value is negative 1.15, then the area you have that corresponds to that Z value, that area in the tail is 12.51%. So essentially, any question that wanted to ask us, what's the probability of an X value being below a certain point? And if it turns out that when we convert that X value to Z, that Z value is negative 1.15, that area under the curve would be 0.1251. In other words, 12.51%. That would be the probability, or the size of the area in that table. Now, the table, when we start looking at positive values, essentially our Z value is just moving from the left side over to the right side. That's all. So when it's 0, you see we have that area will be 50%. But if we have 1.25, 1.2, and I'm just using 5, then that shaded region would be 0.8944. 0.8944 would be the size of this region. Now, if this is 0.8944, the balance in the tail would be 0.1056. 0.1056. Yeah? Because all we have to do is to subtract from 1. Because remember, the total area under the standard normal is 1. And therefore, all we have to do is to subtract from 1. So, folks, I'm going to work a problem right now. And I want you to essentially get your standard normal table. All right?
I just have a question about one of the tables.
Sure.
I can't remember which one it was, but I remember when I was doing my assignment the other night, I was looking at one of the tables and I noticed they were different. Like the one in the I don't know if it's the one in the textbook and the one that's on the formula sheet on Brightspace.
Okay.
But the same.
I'll have to double check the one that's posted in Brightspace, but it should be the same as the one in the textbook. If it's not the same, I can replace it. But the one that we will use should be this one right here that you're seeing in front of you, which is
basically that one's in the textbook.
That's the one in the textbook. Yes.
Okay, thank you.
All right, no problem. So let me find a problem to solve for you to show you how we're going to use this. So I'm just going to try to find a sample problem. Just bear with me for a second. And if you have your calculators, you can sort of calculate along with me. It's all good. All right, so let us find resources. .17, and I'm going to just grab the workbook, and here we go. All right. So I'm going to stop the share and put back my iPad, so that way you see what I'm doing. Okay, cool. So I'm taking this problem from the workbook that I think I posted a workbook in Brightspace, where sometimes I pull sample problems from that workbook. It has, I'm not sure if I gave you the version with the solutions already or just the version of only the questions. But I'm going to pull a question out of here. And that question is as follows. I'm not sure why I keep losing my, oh, I know what it is. I'm looking at the wrong spot. Okay, so it's a PDF file. That's why I'm having difficulty. I see. Okay, here we go. All right. So I'm reading a question, and if you look at the sort of workbook problems that I have in Brightspace, it should be chapter 6, and I'm looking at a question that is question 47 on page 293. Now, that's based on the previous version of the book, edition number 12. I'm pretty sure that same question is probably still in edition 13, but maybe for different number. I've not updated, my apologies for not updating the question numbers, but what's more important here is really the questions. And since you will have access to those questions in the workbook. So essentially in that workbook, I am going to do a question which is 293. So question 293. I mean, sorry, page 293. The question is on page 293. Question 47. But that 293 is really the 12th edition of the textbook. So, but that's just to help you identify it within that workbook that I provided in Brightspace. So here's the data for it. I'm going to read it first, and then I'll put some of the numbers down. According to Salary Wizard, the average base salary for a brand manager in Houston, Texas, is $88,592. The average base salary for a brand manager in Los Angeles is $97,417. So assume that the salaries are normally distributed. So you notice that we're saying assume they're normally distributed. So right away it tells us the normal distribution. With the standard deviation for brand managers in Houston as 19,000, and for Los Angeles is 21,800. So I'm going to just put the information down. So what we have is salaries. And for Houston, so the mean salary for Houston, I'm going to use a mu H to be 88,592. Standard deviation of the salaries for Houston is 19,900. Okay. For Los Angeles, so the mu of L, we call L for Los Angeles, is 97,417, 97,417, and the standard deviation for Los Angeles, this is standard deviation for Houston, is 21,800. So 21,800. What is the probability that a brand manager in Houston has a base salary in excess of 100,000? So this question A says, what is the probability, so we denote it by this, that a brand manager in Houston has a base salary in excess of $100,000? So that means X for Houston, our random variable, should be greater than, it says in excess, $100,000. So how do we get that? Remember what we said was that that's a range greater than $100,000. But how we would get this probability is by equating it to a Z value, by saying that this is the probability of Z, a standard normal variable, being greater than, and I use Z0, meaning like observed, just to differentiated from this Z right here. So I need to figure out now, what is this Z0 value? Now let me just draw this for you. So if we were drawing this, we would put the 88,592, and then we would put 100,000 right here. So this is our 100,000. We're interested in this area right here because we want to exceed 100,000. The standard deviation is 19,900. So to get that area, we have to now put the equivalent Z value. We have to find the equivalent Z value. And so this 100,000 has an equivalent Z. So we have to kind of lay them out exactly the same, except that one is the normal distribution, the other one is the standard normal. So it means that if we could find this area right here, that would be our probability right there. So we have to find that Z value. So that 100,000 will correspond to that Z value. Remember, the mean of the standard normal is 0. The standard deviation of the standard normal is 1. Whereas the mean of the original population was 88,592 and the standard deviation was 19,900. So how do we now find the Z value? We find the Z value as follows. Let me just squish that a little bit, make some space. So we would find our equivalent Z, observe, as X minus the mean over the standard deviation. So that is the formula that allows us to convert the normal distribution to the standard normal. My normal variable is X, my standard normal variable is Z. If I have the mean, the standard deviation, and the value of X, I could get the Z value. So in this case, my Z value would be the 100,000, which is my X, minus what's the mean of that distribution? 88,592. Over what's the standard deviation? 19,900. If we compute what that is, then we should get a value of 0.57. So you could use your calculator to verify that. 0.57, which means that I need to figure out what is the area associated with 0.57. Now, because that 0.57 is positive, remember when we look at the table, it will give us this area right here. So it turns out currently that this Z value is 0.57. When we look up our table, it will give us this value shaded in white. So let's see what that is. So I will call that the area associated with the Z value. Area associated with 0.57 is equal to, so we have to go to our table. Folks, just if you have the table in front of you, just go look up Z is equal to 0.57. I'm not going to bring back that screen. I'm just going to go to the table which I had open earlier. Let's see here, the Z table. So when I look up the 0.57, remember it's positive, 0.57, it turns out that the area that in white is 0.7157. This is equal to 0.7157. So if the area in white is 0.7157, right? If that area is 0.7157, then the area that I'm looking for, which is the area in red, how do I find it? Well, that area would be 1 minus 0.7157. Why? Because the total area under that curve is equal to 1. So the probability of X greater than or equal, so not greater than or equal to, but just greater than, let's undo this, greater than 100,000 is equal to the probability of Z being greater than 0.57. And to get that, I must take away from 1.7157, which then gives me 0.2843. That's my answer. 0.2843 or 28.43%. So that's how we would actually calculate that. All right. If I wanted the probability of, say, the salary being less than, say, $60,000, then I just repeat the process, but this time my Z value will be negative. And then we go to the table in much the same way. So if you know how to go to the table for the positive Z value, all you need to do is to use the table for the negative Z value, and then you should be fine. So let me see what the second question is here with regards to this example. The second question basically says, what's the probability that a brand manager in Los Angeles has a base in excess of 100,000? So the same question, except that you're now going to use the data for Los Angeles. So I will let you work that one out, okay? I will let you work that one out. I'll do one with the less than, so that way you see that one done. So part C to that question. So part B basically asks for 100,000, but using Los Angeles data. Part C says, what is the probability that a brand manager in Los Angeles has a base salary less than 75,000? So brand manager in Los Angeles has, and I put L here to represent Los Angeles. Oops. Less than 75,000. So remember, every X has an equivalent Z, so you could just write that this is probability of Z less than Z0. So I got to figure out what that Z value is. And if I draw the diagrams, I'll just probably do one more like that where I show you what I'm looking at. So remember, this is 88,592. So therefore 75,000 is lower than that. And the area therefore I'd be interested in would be this area right here. Okay? So the equivalent Z value would be, if I'm doing standard normal, remember that's 0. So I must find my Z0, which corresponds to this. And it would be the same green area right here. So whatever that turns out to be, that's my probability. So to find that Z value, I would then need to go Z0 is equal to 75,000 minus, oh, sorry, but I'm using Los Angeles values, not Houston. So somebody should mention that to me. Mistake, so I got to take this out because I'm not using Houston values. The question asks for Los Angeles. So I have to use the 97417, and a standard deviation of 21.8. All right, my apologies for that. So that is 75,000 minus the 97417 divided by the standard deviation, which is 21,800. It turns out that that is, it turns out as negative 1.03, negative 1.03. So now, when we go to look that up, it turns out that the area we will get under the curve is precisely what we are looking for. In other words, the curve will give us the area to the left of the Z value, which is exactly what we want. We don't have to do 1 minus in this case. So let's go ahead and take a look at that. So essentially, we will look up negative 1.0, go over here to 0.03, and find whatever that value is. It turns out that that value is, so I'm looking at negative 1.03, 1.03, which is 0.1515. It turns out that this is, so the probability of Z less than negative 1.03 is 0.1515. And that would be the answer to that question. Right? So that's calculating the probability of being less than a given value. We could always calculate the probability of being in a range. So for example, if I had asked you, what's the probability of being less than, sorry, it being between 75 and 100,000, then in that case, we would have to find, let me just demonstrate that. So if I wanted the probability, let's still use Los Angeles values, which is 97,417, I believe it is. 97,417. Yes, 97,417. And then I'm interested in 100,000 being between 75,000 and 100,000. In that case, I'm interested in this area right here. So if I've already calculated this part to be 0.1515, remember we just calculated it a while ago. So what I would have to do is to find what is the probability that X is less than 100,000. If I find that probability, it will include everything to the left of this value. It will include everything, including less than 75,000. So how then do I find the area in blue? I will have to subtract the probability of X being less than 100,000. I'll have to take away from that the probability of X being less than 75,000, because that probability of X being less than 100,000 will include the probability of X being less than 75,000. So in other words, if I want the probability of X being between 75,000 and 100,000, that would be equal to the probability of X less than 100,000 minus the probability of X less than 75,000. Because the 100,000 contains the 75,000. It includes everything here, including that 75,000, right? So if I know what that 75,000 is and I subtract it from it, I will have the area in blue. Now, we've already calculated this part as 0.1515. Okay, for 1 second, please. So we've already calculated X less than 75,000. What we will need to calculate is X less than 100,000. And I believe, without actually doing the calculations and everything, less than 100,000 gives us, let's see here. It turns out that it is, if I were to do the calculation, so I would have to do, for this part right here, I would have to do Z 100,000 minus the 97,417 over 21, is it 21,800? I would have to do that. If I did that, I would actually get a Z value of 0.12. With that 0.12, it actually has an area to the left of 0.5478. That 0.12 will have an area of 0.5478. You say, well, how did I get that? Well, I'll tell you how. 0.12, if I look at 0.12, how do I get this value right here? So I'll have to go to the table. And if I go to the table, look at 0.12, it will give me the area to the left of the 0.12. So that's all you need to do is to look at that. If you want me to show it to you, I'll certainly show it to you. And here we go. So I'm going to stop sharing and switch over to 0.12, 0.12. Here we go. Let's stop our share for a second. And then share the table. Where's the table? It's right here. So you now have, you see my table. So here's my Z value, 0.12, here's the 0.1. The second decimal place, 0.2. So that area is 0.5478. Remember the shaded region? So this Z is 0.12. So this area completely to the left of that 0.12 is 0.5478. Now remember, we've already calculated the probability of X being less than 75,000 is 0.1515. So therefore the difference, the probability of being between 75,000 and 100,000 would be the difference between the 0.5478 and the 0.1515. Let me just go back now and show that to you. And here we go, back to, so going back here. So I've already shown you that the probability of X less than 100,000 in this case is 0.5478. So which means that the probability of X being between 75,000 and 100,000 is, as I mentioned to you, was the probability of X less than 100,000, which is 0.5478. And remember that includes the X less than 75,000. So I'll have to subtract 0.1515 and see what I get. 15 from 78 will give me 63. 15 from 54, that is 5 from 14 is 9. 2 from 5 is 3. 0.3963. So the answer is that this is equal to 39.63%. And that would be our answer. So the probability of having a salary between 75,000 and 100,000 is almost 40%. So 40% of brand managers in Houston make between 75,000 and 100,000. That's how we interpret that data. 40%, which is a pretty significant number. All right? Good. Okay. So let us do another example now. I think the very final example on that particular topic, and then we'll move to sampling distributions. So let me go back to the question and see what we have. Any questions for me at this point? Please feel free. If I'm moving too fast, let me know. And let's go back to our questions. So this particular question now has a part D, I believe it is, which says, how much would a brand manager in Los Angeles have to make in order to have a higher salary than 99% of brand managers in Houston? Ooh, that's interesting. How much would a brand manager in Los Angeles have to make in order to have a higher salary than 99% of the brand managers in Houston? So let's figure that out. What are we talking about here? So first thing we're going to do is focus on the distribution of salaries for Houston. All right. So distribution of salaries for Houston, remember mu is equal to 88 88,592. And the standard deviation was 19.9. So if you want to make a higher salary than 99% of the brand managers in Houston, it means that there is a value here, which represents that salary, for which the percentage of brand managers making less than that is indeed 99%. So what is that? That entire shaded region will be 0.99. To write this down as a, in mathematical terms, essentially what we're looking at is the probability of x being less than x0 is 0.99. So this is a case where we actually know the probability ahead of time, but we don't know this value. Whereas in the other cases, we ask the question, what's the probability of x being less than a given value? So we know the x0, but we didn't know the probability. In this case, we know the probability, but we need to figure out the x0. So what we know is that this amount right here, 99% of the values in that distribution are less than that. So what we have to do is figure out what that x0 is. So what we know is that every x has a corresponding z. So its corresponding z, let's call it z0, would be whatever that x0 is minus the mean, which is 88,592, over the standard deviation, which is 19,900. All right? X, remember that z is x minus mu over sigma. So in that case, this is the relationship between that x value and its corresponding z. Now, because we know the area to the left of this x0 is 0.99, it means that the corresponding z value is such that the area to the left of it is also 0.99. In other words, if I could draw this here for a second, and there's a z0 that corresponds to that, then the area to the left of that z0, that area is also 0.99. So what z value gives us 0.99 as an area to the left of it? How do we find that? The way we find it is that we have to go to the table, find the area of 0.99 or as close to it as possible, and read off what the z value is. So let's figure out what that z value happens to be if the area to the left of it is 0.99. So we need to actually go and take a look at that. Let's find that out. Let's take a look at the z table. And we want to close our table. Okay, here we go. Acrobat Reader. And I think we should be able to see this table right here. Okay, so here we go. So the area, the shaded region, which represents these values right here, should be 0.99. Let's see if we can find 0.99. So I have to look in the body of the table to find 0.99. What's the closest value to 0.99? Here we go. That's the closest that I could find. 0.9898, so that's 0.000002. But this one is 0.0001. So this one is closer. So if we look at this, what is the z value? It is 2.3. And if I go up here, 2.33. See? So that 0.99, what is it? 0.9901, 2.33. So that z value corresponds to 2.33. All right? So that 2.33, It means that if I know the Z value and I know the standard deviation and I know the mean, I could find the X value. So to find out X value, I just need to manipulate the subject of the formula. So solving for X0, it turns out that X0 will be equal to, if I do a cross multiplication, it will be equal to 19,900.
You share your screen there?
Oh, yes, sorry. Thanks. There you go. So basically, what I've done is to say now that Z value is equal to 2.33, and that 2.33 is 2.33 is the value of the Z. So X0 minus 88,592 over 19,900 is equal to 2.33. So all we have to do now is to make X0 the subject of the formula. And so if we do our cross multiplication and so forth, it will turn out that the 99 multiplied by 2.33. And then what will happen is that the 88,592 gets added on because it has a negative value on the left side. So therefore, we must add it for positive value, 88,592. To compute that, we should get an answer of, I should have the answer right here. That answer turns out to be $134,959. So it turns out to be $134,959. You could do the multiplication and addition for me. But that's the final answer. So in other words, if a brand manager in Los Angeles is making $134,959, they are making a higher salary than 99% of brand managers in Houston. That's what that is actually telling us. They are making a salary that is higher than 99% of the brand managers. If I wanted to say what salary should a brand manager in Los Angeles make to make a higher salary than 80%, then I would just change my area from 0.99 to 0.8, right? So you just basically match it up to. Yes, go ahead, please.
Sorry, when you did the X0 minus 88,592 to get divided by 19,900, 2.33, how did you get 2.33?
Okay, so the 2.33 comes from having the 99% area. So you see that green region. Let me see. Oh, I have to go back to show it to you. But before we do that, let me just show you from the Z table. So what happens is that the area that is the 99% is the equivalent to this shaded region right here. See that shaded region? Mm-hmm. So there's a corresponding Z value for which 99% of the values are smaller than that value. So if that area, shaded region, is 99%, what is the corresponding Z value? So what I have to do is to look in the body of the table, because remember, these values are the areas, right? Mm-hmm. So if I go down here, we see when that area is 0.9901, the Z value is 2.3. And if I go up here, the second decimal place is up here.
Oh, I don't think you switched to the table.
Oh, I didn't? I'm still on my iPad?
It looks like it.
Okay, I'm probably still on my iPad. Let's share this. There we go. You see that now? Mm-hmm. So what I was saying was that the area to the left of Z is 0.99, mm-hmm. right? So that's that shaded region right here. That shaded region corresponds to these values in the table. So if that area, which is the blue region, is 0.99, let me try to find it, which is here 0.990. That's the closest value that I can find to it.
Okay.
And that corresponds to a Z value of 2.3, and there's a second decimal place.
Okay, that makes sense. Perfect. Thank you for explaining.
Good. And then we just put that value in the formula. So that will be the Z value, 2.33, and then the only unknown we have is the X value. So that X value corresponds to that Z value of 2.33. So based on that distribution, it turns out that that X value is 134,959.
Perfect, that makes sense. Thank you.
Great, no problem. So that actually kind of rounds things out for us in terms of just manipulating the normal distribution. The other things that we have to do in chapter 7 now is based on the normal distribution, but we are going to introduce something called sampling distributions. So before I go any further, any other questions on the normal distribution? And if not, then I'll introduce you to sampling distributions. All right, so, okay, so no questions at this point. Let's get into the topic of sampling distributions. What's that all about? So we're going to stop share and share my PowerPoint with you. It would be nice if we could have multiple screens and just flip between them, but we have to start, share, unshare, reshare. So it does take a little bit of time. So bear with me. PowerPoint chapter 7. So here we go. So introducing you now to chapter 7, sampling distributions. Can everybody see that? You see sampling distribution of P bar? Does everybody see that?
I can see it.
Okay, fine, good. So let's try to get a sense of what that's all about. So first of all, let's get a sense of what do we mean by sampling distributions. So a sampling distribution now, so okay, let's go back. The normal distribution that we just talked about in chapter 6, there's no sampling involved. All it is that we have some information on the population, and we're told that, say, the average salary of a brand manager is X, the standard deviation is this. What's the probability that an individual makes more than 100,000 or an individual makes less than 75,000? We're not sampling, we're just interested in one individual. But now sampling distributions involves taking a random sample and now asking the question, like, what is the probability of us observing a sample statistic? So in that case, we often are interested in two types of sample statistics at this point. One, which is called the sample mean, which is X bar, and the other one is called is the sample proportion. So we have those two situations where we are interested in the probability of observing a particular sample mean or the probability of observing a particular sample proportion. And so how do we actually do that? What happens when we are now interested in the value from a sample as opposed to just an individual? So that brings us to a topic called sampling distributions. So let me try to introduce you to this concept. But there are a couple of things that we need to be aware of, right? So one of the first things that we need to be aware of is similar terminology. There is point estimation. And so a point estimate is whatever we observe in a sample. So if I take a random sample of, say, 20 brand managers, just to use that example, and the 20 brand managers have an average salary of, say, 85,000, that is a sample statistic, right? So we call that a point estimate. Why? Because that sample mean is estimating for us the population mean. And then we will also calculate in that sample of 20 brand managers the sample standard deviation. We could do that from what we learned in chapter 3 about how to calculate sample standard deviations. And that would also be a point estimate of the population standard deviation. So one of the concepts to keep in mind is that anything that you observe in a sample is an estimate of its equivalent population parameter. So if I observe a mean in a sample, that's an estimate of a population mean. If I observe a standard deviation, that's the estimate of the population standard deviation. If I observe a sample proportion, that's the estimate of the population proportion. So point estimates are essentially what we observe in a sample, and they are basically estimates of the equivalent population parameters, right? So that's, we call them point estimators or sample statistics. So that's one. Let's see if we can get to the idea of what a sampling distribution is. So what happens now is, in terms of the concept of a sampling distribution, if I took from the brand, let's just stick with the brand manager's problem for now. If I took a random sample of a given size, let's just stick with the 20 brand managers, and let's just pick one of the locations, Houston. So if I were to take a random sample of brand managers from Houston, I will observe a sample mean. I don't know what that is going to be, but let's just say it's 65,000. If I took another sample, again, of 20 brand managers, I will observe another mean. And if I keep taking as many samples of 20 as possible, I will get different sample means. Every time I take a different sample, I get a different sample mean. So what happens is the collection of all those possible sample means form what we call a distribution. The same way the collection of all the salaries of all the brand managers form a distribution. The collection of all of the sample averages for taking 20 brand managers at a time, the collection of all of that forms a distribution that we call a sampling distribution. And if you put the words together, it's a distribution because it's just a collection of values, but how did we obtain it? Through a sampling process. So we call that a sampling distribution. So you can see here a simple random sample. If we have a population mean, a simple random sample of n elements is selected from the population, basically a sample size, and the sample data provide a value for the sample mean. If we keep taking as many of those as possible, we will generate a sampling distribution. So the value of x bar is used to make inferences about the value of mu. That's basically the sample estimate makes sample value makes an estimate of the population value, right? And so that sampling distribution is of interest to us. What is the shape of it? And we have a couple of theorems that tell us a little bit about the shape of that. One is called the first limit theorem. And I'll sort of kind of go back to my iPad to kind of show you in terms of a schematic what we're talking about. But the sampling distribution of x bar, what it means is that if I took all of the sample averages, what does the shape of that distribution look like? It turns out that if my population is normal, the shape of the sampling distribution of the sample means will also be normal. And that theorem is called a first limit theorem. And that's important to know. And we'll come to that very shortly. There's another theorem called the central limit theorem, which is a very important theorem in statistics. What it says is that, well, if I don't know what the population looks like, if the population is not necessarily normal, what does the sampling distribution look like? In other words, if I generated as many possible samples of size n, and I observe the sample mean, what's the shape of that distribution? Well, the central limit theorem tells us that if we keep making our sample sizes larger and larger, then the shape of that distribution will start to look like a bell-shaped curve, which is an interesting phenomenon, because what happens is that if we consider sampling distribution as a normal distribution, then we could do what we did in chapter 6 with it. But for us to be able to do that, or to say that, we need a special condition, particularly if we don't know if the population distribution is a normal one. If we don't know if it's normal, then we have to make sure that the conditions exist so that the sampling distribution looks like a bell-shaped curve. And that condition is to make sure that we have large samples. You see here? So in selecting random samples of size n from a population, the sampling distribution of the sample mean can be approximated by a normal distribution as the sample size gets larger and larger. And then you could ask me the question, well, when is it large enough? And that point is typically when the sample size is greater than or equal to 30. We tend to use 30 as a benchmark, that by the time the sample size gets to 30, it's getting larger and larger, all right? So that's a central limit theorem. Let me, in terms of pictures, demonstrate to you what we're talking about in terms of sample distribution. Okay, so here we go. So the basic idea is something like this. I'm just going to show you in terms of like pictures what that means. If we have a population has a mean mu, standard deviation sigma, if I were to take random samples of size n each time, if I took a sample of size n, I will observe a sample mean and a sample standard deviation. If I take another sample from there, if I take another sample, same size, I will observe another sample mean called x bar 2, that's 2. And if I keep taking another one, it will be x bar 3, s3, etc. So the collection of all of these values, x bar 1, x bar 2, x bar 3, x bar m, however many we took, that is a distribution. And that distribution is called a sampling distribution. Well, that sampling distribution, I could find its average. But notice now, I am dealing with sample means. So I could take the average of the sample means, which is mu of x bar, if I have all of them in the population, and I could take the standard deviation of the sample means called sigma x bar. So all of these are, even though I represent them by x bars, they're just numbers. So I could find an average of any set of numbers and a standard deviation of any set of numbers. So which means that of all of these x bars, if I have all that I could generate, then if I average them, I will get the average of that distribution. In other words, there is a distribution for those sample means, and that's the average of that distribution. And there's a standard deviation. Question is, what are those values? And if we apply the first limit theorem, which basically says that the population is normal, guess what? The sampling distribution also looks normal. It's like this. That distribution will look like that. It will have a mean, mu x bar, and sigma x bar. It turns out that mu x bar is equal to the same mean of the population, but the standard deviation is the standard deviation of the population divided by the sample size, right? That's the relationship between the sampling distribution and the population distribution. So if we apply the first limit theorem, that's what we're going to get. And remember, for every normal distribution, there is a standard normal. Well, what is that standard normal again? If you may recall, the standard normal was always z is equal to the variable, but now our variable is not x anymore, it is x bar. So it's x bar. What's the mean of the sampling distribution? Mu x bar. What's the standard deviation of that? Sigma x bar. So it looks just like the first one, except that instead of saying x minus mu over sigma, we're now saying x bar minus mu x bar over sigma x bar, referring to the sampling distribution, all right? But because we know from statistical theory that the mean of that sampling distribution is same as the mean of the population, and it could be proven, but we're not going to prove it as part of our course. So it will be x bar minus mu, same as the population, but remember the standard deviation is the population standard deviation divided by the square root of n, so we could represent it this way. So now the z value is calculated as x bar minus mu divided by sigma over root n. And that's the z-score for sampling distribution of x bar. All right? So first limit theorem basically says if the population is normal, sampling distribution is normal, and that's what your z value is equal to. If we were applying the central limit theorem now, is it any different? The answer is no. Because remember, the central limit theorem says just make sure the sample size is large enough. And if the sample size is large enough, then the sampling distribution of the sample mean will also be approximately normal. So that will be the random variable. It will be mu x bar, sigma x bar. So that will be the sampling distribution, but we have to make sure the sample size is n is greater than or equal to 30. That is large enough, all right? So once that's the case, we have exactly the same relationship because mu x bar will be equal to mu and sigma x bar will be equal to sigma divided by the square root of n, which then gives us z is x bar minus mu sigma over the square root of n. So we get exactly the same z formula, whether or not we're applying the central limit theorem or we're applying the first limit theorem. And folks, everything that we did with the normal distribution in chapter 6, we can do here, except that in chapter 6, our variable was x. Now our variable will be x bar. So instead of saying probability of x greater than or equal to 30 or something like that, we'll be saying probability of x bar greater than or equal to 30, which means probability of the sample mean that we observe is greater than 30. So that would be the difference between the two. The random variable is x bar in terms of the sampling distribution. The random variable is x in terms of the population. So that's the difference between those two things right here. So let's try to find a problem to solve. Quickly, we'll do one example. And then we will get into the sampling distribution of the sample proportion. So let's see what I have for a problem with that. I'm going to go to the same workbook that I have in Brightspace, and I'm going to grab a question from here. Let's see here. What's the probability to propose proportions? Okay, we're going to go here. All right, so the question I'm going to do is as follows. In the workbook, if you go to the workbook, it's chapter 7, and the question is question number 24. I will read the question for you, but I'll show it to you right here as well. I'll do a new share. It should allow me to switch between them. All right, so here we go. So it is this question right here. Barron reported that the average number of weeks an individual is unemployed is 17.5. So that's like a population. Assume for the population of all unemployed individuals, the population mean length of unemployment is 17.5 weeks, and the standard deviation is 4 weeks. Suppose you like to select a sample of 50 unemployed individuals. Notice that? A sample of 50 unemployed individuals. So we're selecting a sample now. The sample, for a follow-up study. Show the sampling distribution of X bar, the sample mean average for a sample of 50 unemployed individuals. So essentially, what this question is asking us to do, and I'll just use the data, and I'll go a little more broader than what we've been asked. Essentially, if the population mean unemployment duration is 17.5 weeks, and the standard deviation is 4 weeks, right? What is the sampling distribution? But we're told, I believe, that, are we told that the population is normal? It says, we're not told anything about the population. If we read that, assume that for population of all unemployed individuals, population mean is 17.5 weeks, standard deviation is 4. Suppose you like to select a sample for follow-up study. Show that the sampling distribution of X bar. So notice we have not been told anything about the population distribution. Okay. See, pause share. Well, resume my share. Hang on 1 second, folks. I see something about pausing. Shares pause, bring my window to the front. What does that mean? I will do this and then share again. Come back here. Okay. So this is the question I'm working with. So what is the sampling distribution? So essentially, because that 50 is larger than 30, I could apply the central limit theorem and say that the sampling distribution is a normal distribution, all right? And the mean of that distribution will be the same as the mean of the population, which is 17.5 weeks. The standard deviation of that distribution will be the standard deviation of the population divided by the sample size. Remember, we have sigma over root n, so it will be that the population standard deviation divided by the sample size. And so that will be the sampling distribution of X bar. And then we could find probabilities with it. So let's do that. Let's do an example here. So I'm going to go to my iPad. All right. So for this question, the data that we have is that the mean unemployment is 17.5 weeks. The standard deviation is 4 weeks, right? So our sample size was 50. What is the sampling distribution? What is the sampling distribution? Well, in this case, we will say that the sampling distribution of X bar, actually I should be more complete by saying, what's the sampling distribution of X bar? So the sampling distribution of X bar, we could denote it like this, will be a normal distribution with a mean of mu X bar and a standard deviation is sigma X bar. So I'm introducing a little bit of notation, which is more like a shortcut notation. So that tells you X bar is a normal distribution with a mean mu X bar, sigma X bar. But because our sample size is greater than 30, central limit theorem tells us that the mean of X bar is the mean of the population, which is 17.5, and the standard deviation of X bar is the standard deviation of the population divided by the square root of n, which is 4 divided by the square root of 50. And we could figure out what that is. And so we would have a normal distribution with a mean of 17.5 weeks and a standard deviation of 4 divided by the square root of 50. That's the first part of that question. Second part of that question wants us to find a probability. Part B says, what is the probability that a random sample of 50 unemployed individuals will have a sample mean within 1 week of the population mean? Within 1 week of the population mean. So in essence, what we're being asked for is what's the probability that that sample mean will be within 1 week of the population mean. If it's within 1 week of the population mean, well, remember the population mean is 17.5. So if it is within 1 week, the upper limit would be 18.5, and the bottom limit would be 16.5. That allows you to be within 1 week of the mean. So if I take 17.5 plus 1, that gives me 18.5. 17.5 minus 1, so that's within 1 week. So that's what we essentially are looking for. And to find that, if we actually drew that diagram, essentially what we're looking at is the mean is 17.5, we want 18.5, and we want 16.5. And the nice thing we know is that that's symmetrical. Why? Because it's within 1 week. So we added 1 week to the 17.5 and we subtracted 1 week from the 17.5. So we want this area right here shaded in green, red and green, all right? So how do we find that? We must now go and do exactly what we did before, find the Z value and go to the normal table. So let's find the Z value associated with this one. And what would be interesting is that if we find the Z value associated with one of them, because they're the same distance from the mean, one would just be the negative of the other. So let's just find, I'm going to refer to the Z value associated with this one as Z1, and the Z value associated with this one as Z2. So Z1 is equal to 16.5 minus 17.5 over 4 divided by the square root of 50. All right? Because remember, our Z value is X bar minus mu sigma over root n. Because we're dealing with a sampling distribution and not the population distribution. So let's figure out what that is. It turns out that that value is negative 1.75. Negative, we could actually do the calculation, negative 1.75. So Z2 now at 18.5 minus 17.5 over 4 divided by the square root of 50. Well, remember the numerator will also be 1 over 4 divided by the square root of 50. They're the same distance from the mean. So it just means that this would be positive 1.75. Right? So that's the Z value in both cases. As a result, we can write that the probability of X bar being between 16.5 and 18.5 is the same as the probability of Z being between negative 1.75 and positive 1.75, right? That is the same probability right here. And so what do? We actually go to the Z table, find this probability, and subtract from it this probability right here. In other words, that would be equal to the probability of Z less than or equal to 1.75 minus the probability of Z less than or equal to negative 1.75. In other words, we have to subtract the smaller from the bigger one because the big area will contain the small area, like we did with chapter 6. So let's find what that is. If you go to the Z table and look up 1.75, that area will be equal to 0.9599. So that is 0.9599. The area associated with negative 1.75 is, and it turns out to be 0.0401. 0.0401. So when we subtract those two values, we get 0.9198. 0.9198. If you just use your calculator quickly and verify that. So it means that the probability that a random sample of 50 unemployed individuals will have a sample mean within 1 week of the population mean. Otherwise, we can say it as the probability that that sample mean will be between 16.5 weeks and 18.5 weeks is 91.98%. In other words, 91.98% chance that if I take a random sample of 50 unemployed individuals, the average time that they wait, or the average time that they are on unemployment, is between 16 and a half and 18 and a half weeks. So that's what this is actually telling us. Okay? Good. And if we wanted to do other things like say, well, what's the probability that the random sample will be greater than or equal to, say, 19.5 weeks? In that case, all we have to do is to calculate the area associated with 19.5 weeks, subtract it from 1, and we'll get the tail. Or we could ask the question, what's the probability that that random sample will have an average of less than 16 weeks? So we could actually calculate this. If you know how to calculate any one of what we've done before, all you have to do is to find the corresponding Z value and know what area you are interested in. So in this case, we are interested in, if this is 19.5 and this is 17.5, we are interested in this area. So we'll find the area in the table, which will be the dotted region right here, subtract it from 0.1, and we'll get this area right here. If we're interested in less than or equal to 16 weeks, so this is 17.5. 16. So this would be the area that we're interested in. I guess I've been talking for too long. And so that would figure out what that area is once we calculate the corresponding Z value or the corresponding Z value. So if you understand one of them, the principle of one, you could essentially replicate that for any situation. Okay, so that gives us the sampling distribution of the sample mean. I want to end with the sampling distribution of the sample proportion. So let's see what that looks like. Sampling distribution of the sample proportion. Let's go back to, so we're still sharing my iPad, so let's go to the next. So in much the same way that we generated a sampling distribution for sample mean, we could generate a sampling distribution for sample proportion. So for example, let's say if in the population, approximately 8% of people were unemployed. So population proportion P, that's our parameter, 8% of people are unemployed. So that's P is equal to 0.08. If I generate samples of a given size, let's just take the same 50. If I generate samples of a given size from that population, every time I generate a sample, I will get a different sample proportion. Let's call it P bar 1. So we use P bar to denote sample. If I generate another sample again, P bar 2, P bar 3, P bar 4, etc., P bar M, however many we generate. So if we generated all the possible proportions, guess what? We could find, remember that these are just values. So we could find the mean of the sample proportions. And we could find this kind of deviation of the sample proportions. But what is that equal to? We apply a principle by the binomial distribution where we say, if the sample size times P, which is the 8% in our case, is greater than or equal to 5, and the sample size times 1 minus P, is also greater than or equal to 5, we could use what we call a normal approximation to the binomial. That means that, you know, if you remember from 1206, a binomial distribution is when you have a random variable taking on one or two values, yes or no. You know, black or white, broken or not broken, working or not functioning. So in that case, the binomial distribution can be modeled as a normal distribution. And it so happens that for that normal distribution, the mean of that normal distribution will be the same as the population proportion, but the standard deviation will be given by the population proportion 1 minus that proportion divided by n, the sample size. That really comes from the binomial distribution. You don't have to prove it, you just have to live with it. And the z value for that distribution, remember, is always the sample value that we observe. What's our sample? P bar. What's our population? P. And what's our standard deviation? Sigma p. Right? So I could replace sigma p now, P bar minus P by P1 minus P bar, sorry, P1 minus P, not P bar, sorry. Take out that bar, we don't need it. And over the square, over n. And that becomes our z value right here. So let's do a quick question involving that. In much the same way that we've applied the normal distribution already, we're applying it again in much the same way. So once you know how to do one, you could do the rest. So even though we're introducing a new random variable, which in this case is the sample proportion, in the last one we introduced the variable sample mean, the principles are the same. So as long as you know how to apply the normal distribution, all you need to know is what are the different parameters you're using. So in this case, it would be sample proportion, population proportion, and the standard deviation, given by this formula right here. So let's do a question. And that should bring us to a close. So we're almost there. Bear with me. Let me try to find a question very quickly. All right, so here's a question that's interesting. It's still in chapter 7, and this is question 37 in the workbook. Chapter 7, question 37. So chapter 7, question 37 in the workbook. And I'm going to quickly go over that question with you. So let's look at that question, and I'll do a piece of it, and then we'll be done. So we're told that people end up tossing 12% of what they buy at grocery stores. We buy all kinds of food, and then we have to throw it away. So 12% of what they buy at grocery stores. Assume that this is the true population proportion. So when we say true population proportion, we're saying assume that that is P. So P, for our problem, is 0.12 or 12%. It says show the sample distribution of P bar, the proportion of groceries thrown out by your sample respondents. Now we're told that the company, we plan to take a survey of 540 grocery shoppers to investigate their behavior. 540 grocery shoppers to investigate their behavior. All right? So let's look at that. So our sample size is, I'm going to switch speed just now. I'm just going to write the information down. 540. Okay? So let's see here. We're going to switch screens one last time. And we're going to do Here we are. Cool. Okay. So there we go. So remember that the question is about people throwing away stuff from the grocery shopping. 12% of people throw away stuff. Our sample size is 540. So what is the sampling distribution of the sample proportion? P bar. So if we take a random sample, we will observe P bar. What is the nature of P bar? Well, P bar should be a normal distribution with mu P bar, sigma P bar, where we know mu P bar is equal to P, in this case equal to 0.12, and sigma P, sorry, mu P bar, sigma P bar is the square root of P 1 minus P over N. So it would be the square root of 0.12. 1 minus 0.12 would be 0.88 over 540, whatever that turns out to be. Now, why did I assume that this was going to be a normal distribution? Remember what we said is that if the following condition holds, then we can use a normal approximation to the binomial. What's that condition? N times P must be greater than or equal to 5, sorry. Or N times 1 minus P must also be greater than or equal to 5. So let's do a quick test. What is our N? 540. What's our P? 0.12. Well, we know 10% of 540 is 54, so 12% of 54 will definitely be greater than 5. And then 1 minus P is 88%, 0.88, times 540 will definitely be greater than 5. So since that condition is satisfied, then we could assume that the sample proportion is a normal distribution. And if it's a normal distribution, the mean will be given by this relationship right here, standard deviation given by this relationship, and finally, the Z value would be sample statistic minus the population parameter, which is P, divided by P 1 minus P over N. So that would be our Z value right here, okay? So for this particular question, I could ask the question, what is the probability that in a random sample of 540 individuals, 15% or more throw away their food or throw away the groceries? So that would be our last question. And you could always do it for less than that and so on. So it would be, what is the probability that P bar is greater than or equal to 0.15 if our sample size is 540? So in this case, is the probability of Z greater than or equal to Z0. But what is that Z0? It's P bar minus P, P1 minus P over the square root of N. But what is our sample proportion? In this case, it will be 15%, 0.15, minus population, 0.12. And you would have to now take the 0.12 times 0.88 over 540, all right? Which basically gives us 0.03 over whatever that denominator is. I did not calculate this one, and I have, so if somebody could help me out faster than I can, I'm going to try to see if I could do it on my phone, since I don't have a calculator with me right here handy. And let's see if I could do this. Really. Somebody have an answer for me much more quickly than I do, it would be great. And we want square root, open bracket, 0.88 times 0.12 divided by 540 square root. Okay, I think and then if I take the inverse of that, multiply by 0.03, what do I get? Oh, my answer is crazy. Does anybody have an answer for me? Square root of, I'll find it in Excel. Give me a second. Is equal to SQRT square root of 0.1, sorry, 0.12 times 0.88 divided by 540. And let's see what we got. Okay, so if I take this now, so this turns out to be 0.03 divided by 0.013984. 0.013984, which then this is equal to 0.03 divided by this value. Bear with me. 2.15. This is 2.15. So that's the Z value associated with this question right here. And so now to find the probability of Z greater than or equal to 2.15, I must do this. So I will have 2.15 as my Z value. Remember, this is 0. So the table will give me this area. And since I'm looking for the green area, which is greater than or equal to 2.15, I must subtract the red area from 0.1. Sorry, not 0.1, from 1. So let's see what that red area turns out to be. I won't switch to Z value, to the Z, I mean, the screen, to the Z table, and you know how to use it. So I'm just going to give it a value. So when Z is 2.15, the area is 2.15, 2.1, here we go. So 2.1, the area is 0.9842. 0.9842. So if that area is 0.9842, then this area has to be 1 minus 0.9842, which gives us 0.0158. So our answer is that this is equal to 1 minus 0.9842, 0.0158. Answer 1.58%. All right? So, having said all of this, this particular question here, we're saying that the probability that in a random sample of 540 individuals, that 15% or more of them discard groceries or whatever, right? So the probability of that happening, that 15% or more discard their groceries, is 1.58. That's not a very big probability. It's less than 2%. In other words, there's a less than 2% chance that in a sample of 540 individuals, right, that 15% of them toss their groceries. Okay? Throw away their groceries or throw it out or whatever it is, maybe it gets bad. So we've actually calculated that. If we wanted to do, what's the probability that in that same sample, that 10% or less of them then we just repeat the process by using p bar is equal to 0.1, right? As opposed to the 0.15 that we used earlier. So you could certainly just manipulate the formula appropriately depending on what the question is asking for, all right? So that is sampling distributions of the sample proportion, all right? So when you see questions like, what is the nature of the sampling distribution, or what is the sampling distribution of p bar, you usually have to give the mean of that distribution, which is basically the same as population proportion, which is p, and the standard deviation, which is the square root of p into 1 minus p over n. So the square root of that. You just calculate those values, and then you answer that. So for example, for this question, I would have given, if I was asked, what's the sampling distribution of p bar? I would say, well, the mean of that is the same as the mean of the population, which is 0.12. The standard deviation of it, p bar, is basically the 0.013984 that I computed earlier, all right? That's essentially what we would have done with that. Okay, so I think that brings us to the end of what we want to cover, and we sort of pretty much caught up in terms of sampling distributions, the normal distribution, and we should be able to do this. Remember, as a support for you, that in MindTap there are some videos as well. So while I have my own videos with additional problems, so if you watch those, the normal distribution and then sampling distribution of X bar and proportion, so you have those in terms of my playlist and the YouTube videos. In addition to that, you have the videos in MindTap that can help you. Okay, so please take advantage of that. And last but not least, I actually recorded this session. So once it's done, I will post the link again to the session. It's almost 2 hours long, so it might be difficult watching a 2-hour video, but for those who missed the class, certainly watching the lecture again might be useful. You could try to skip through it or whatever it is. But it will be, once it's processed, I will make the link available so people could actually download it or simply watch it if they need to again, all right? Good, any questions for me before we say goodbye? It's actually 9 o'clock on the dot. Good timing. Was that helpful? Folks, anybody, was that did I explain the concepts well enough? Did you understand what we discussed?
I understood.
Thank you, Callie. Okay. All right. So I will make the link available once. It takes a little while to process once I stop, and then we take it from there. I see a comment in the chat. Okay. Thank you, Catherine. Okay, great. So on that note, if you have any questions, you can send me an email. If you want to arrange for a Zoom meeting one-on-one, we certainly can do that. Just send me an email. Now, granted, allow for a little bit of time. You know, I know sometimes we send an email right away and we expect a response right away. Please allow for a day or two before I respond, because I have so many other emails that keep coming at me all the time. And so everything has to get prioritized, and you have to make the time to be able to respond. So it might take a day or more before I can respond properly to you, okay? So give the questions in MindTap a shot. You have some practice problems. If you could set aside some time to try it out and see how that works out. And if you're having difficulty, then let me know. But hopefully between this video, my YouTube videos, and the MindTap videos, you'll have plenty of support to help you understand the concepts, okay? So on that note, if there are no other questions, then I bid you good night, okay? Okay, thank you, folks. Bye-bye.